Hello everyone, and now we will discuss the auction or second portion of the problems of the problem set 7. And right now we will discuss the first problem of the auction part, which is about these finite types, where we have a first price sealed bid auction. This basically means that if you say that you bid 7, if you get lucky and you win, you pay 7, exactly 7. So there's another type of auction which is called the second price sealed auction. And in that case, if you bid 7 and the other guy bid 5, you win and you pay 5. So that's the difference between first price sealed and second price sealed. In second price sealed, you pay the second highest price when you win. In first price sealed, you pay the price you said you pay if you win. So we are given this table with valuations and corresponding probabilities. So each bidder knows their own type or valuation. However, they could have 4 potential valuations. So it's like you could be in 4 different situations, and you know that you're in this situation, so you know your valuation. And for each of these situations, they have to have a strategy, or they have to have some bid. So for when they have valuation 10, they will have some bid 1 or A. When they're in this situation, they will have some bid 2 or B. If they're in this situation, they will have some bid 3, or let's denote it by C. And when in this situation, they will have some bid 4, and that's D. So a combination of all this is their strategy. However, they don't know the other bidder's valuation. And because of that, they don't know what the other bidder is bidding. However, now they're telling us that we should buy in the symmetric Bayes-Nash equilibrium. So let's say strategy of player 1 is this. Then if we want it to be symmetric, the strategy of player 2 would be the same. So it would be B1, B2, B3, B4, right? So now you can assign probabilities to this. So probability that they will bid bid 1 is 0.2 because this is the probability of valuation 10, probability of bid 2 is 0.3, probability of bid 3 is 0.4, and probability of bid 4 is 0.1. So imagine now that your valuation 10 and you're bidding bid 1. With 0.2 probability, you guys tie, so you actually have 0.1 probability of winning, because when it's a tie, there's a coin toss, so you win 1/2 of the time out of this 20%. So you have 10% of winning chance. If you're up against this guy, you lose because they bid more. If you're up against this guy, you lose. If you're up against this guy, you lose. So your probability of winning would be this. If they are type 2, when this guy is type 2, you bid 2, B2. So if suddenly the other guy's type is B1, your probability of winning is, well, 100%, but the probability of this guy is 0.2, so there's 0.2 probability of winning. Then if you're up against valuation 12 guy, they will beat B2, so you win half of the time, so 0.15 will be added to your winning chance. In case of B3 and B4, you lose, so 0, 0, so your winning chance is 0.35, and so on. That's how it looks like. And apart from winning chance, you're also interested in the payoffs, right? So for each bid, there's a corresponding payoff to it. So if your valuation 10 and you bid B1, your payoff is 10 minus B1. However, only when you win. So you are interested in the expected payoff of winning. So if you look at here, your probability of winning was 10%. So your expected payoff of playing bid 1 when you have valuation 10 is 10 minus B1 times 0.1. And now there come in some incentives for deviation. So what if you increased your bid by 1, for example? So let's say you bid B plus 1, but let's assume that it's less than B2. If you do this, you definitely beat the 10 valuation guy because they're bidding B1. However, you don't bid B2, B3, or B4. So your probability of winning is 20% now. So basically you doubled your chances. However, now your payoff is 9 minus B1. So it's like 10 minus B1 plus 1. So you get this. So you reduced the payoff of winning. However, you increase the chance of winning. So there's a chance that you just increase your expected payoff. For example, if you bid 1 before, so here you had 9 times 0.1 and you had 0.9 expected payoff, and now you, instead of bidding 1, you bid 2, your payoff is actually now 10 minus 2, so 8 times 0.2, and it's 1.6. So in such a scenario, you would deviate. So the basic idea is that for any B1, there could be some other bid which increases your chances and therefore increases your payoffs. Or conversely, if you're this guy with the higher end of the valuation and you're bidding like 20, if you're bidding 20, so before is 20, your payoff is 0 because your valuation is 20, but you will be paying 20, so you will be getting nothing. So wouldn't it be better to just reduce your bid to 19? If you reduce your bid to 19, you will get 1 payoff if you win, and the probability of winning is actually 0.2 plus 0.3 plus 0.4, but not this, because you lose to this guy now, because you reduced the bid. So, but it's still 0.9, and you get 0.9 payoff. So basically, the basic idea is just, is there another type of bid other than the strategy that is just better for me? And if such a bid exists, then this is not a symmetric Bayes-Nash equilibrium. So to find the symmetric Bayes-Nash equilibrium, we have to test combination of strategies at which there are no better bids. So they're not better off, so they do not deviate. I have actually prepared something in Desmos. So this A, B, C, D, let's imagine this is bid 1, bid 2, bid 3, and bid 4 for the different valuations. And now I have created functions, so you can call these payoff functions, but these are expected payoff functions. For example, this is the expected payoff of valuation 10 guy when they bid 8, while the type 2 bids 10, type 3 bids 12, and type 4 bids 13. The reason I created these Desmos functions and stuff is to make the search process easier, because generally what you have to do is just pick one set of strategy and then test it to see if it's a Bayes-Nash equilibrium or not. But here it's actually easy to find a Bayes-Nash equilibrium. So let's just choose some random numbers, and I can highlight the points where the bids are integers. So for example, 3. So let's say player 1 is bidding 3. Well, both players are bidding 3. So in this case, the payoff is 0.7 for both bidders. But if one of the bidders deviates, so the other bidder is bidding 3, but you bid 4, you're actually better off. So in cases when A is 3, this is not a Bayes-Nash equilibrium. So let's increase this bid. And if you look at here, again, if you bid 4, your payoff is 0.6, but if you deviate, your payoff is higher, 1. So this is not a Bayes-Nash equilibrium either. We increase this again, voila. So, sorry. So here, the payoff is lower. Here, payoff is higher. So not a Bayes-Nash equilibrium. This looks like a Bayes-Nash equilibrium. No, sorry. So here it's 0.4 and here it's more, so it deviate. We increase this again. So here it's 0.3 and here it's 0.4. You deviate again, so let's increase it. And here it's 0.2, here it's 0.2. They will not deviate. So we can just keep this here, or we could increase it again to see what happens. So here it's 0.1 and here it's 0. They do not deviate. Well, okay, let's pick this one. So let's say A is 9. So may have found the equilibrium value for bid 1. Now let's look at valuation 12 guy. So now we are at when they're bidding 11. So if they're bidding 11, their payoff is 0.35. When they're bidding 10, it's 0.4. Huh. So it's actually not a good idea to bid 11 because they would deviate to bidding 10. So you reduce this. And now bidding 10 gives you 0.7. Bidding 11 gives you 0.5. Bidding 9 gives you less. So there are no strategies or actions that are better than bidding 10. So this could be a potential value. We can actually test again player 1 to see if anything changed. However, bidding 9 is still the best option. So again, this is a good one. This seems to be a good one, but we will see. So now we can move on to player 3, map their function. Now it's set to 14, right? So 14 gives you 0.7 when you have valuation 15, but if you reduce it, you're actually gaining. So let's reduce it a bit. Yeah, but so at 13 you get 1.4, but at 11 you get 2, so let's reduce it again. Okay, so at 12 you get 2.1, at 11 you get 2. So actually this is quite good. So this is probably an equilibrium value for C. But let's test again player 2 now, whether he wants to deviate from where he is, because the situation, we kind of changed the situation now. So if we check, 10 is still the best option. Okay, now we can move on to player 4. Now he has it set to a 17, but 17 is actually worse than, for example, 16. Let's reduce it. So 16 is worse than 15. Let's reduce it. 15 is worse than 14. 14 is worse than 13. 13 is the best. So now we have found that 9, 10, 12, and 13 is one of the Bayes-Nash equilibrium of this game. Well, we practically solved it, but what if we do this? 12. Okay, 12 is not a Bayes-Nash equilibrium. And what if I change, for example, A? What if I change A? Let's see. Change A to 8. So this is, so they're indifferent, I think. Sorry. They're indifferent, I think. So this is also a Bayes-Nash equilibrium. Let me look at player 2 now. So yeah, this is a Bayes-Nash equilibrium. But what if I increase this? No, it's not Bayesian. What about this? Okay, so 9 works. So 9 is better than 10. So this works. What about the third type? So 12. Ooh, 10 is better than 12. Let's reduce it a bit. So 11 is the best now. So this works. So 8, 9, 11. And now we reduce it. So 13 doesn't work anymore. Let's reduce it. 12 works. Now let's just test just in case if the other types are still doing the optimal thing. So C11 is no longer optimal. So you see how changing the other person's strategy changed what's optimal for this guy. So it altered it. So, and now like if I reduce this, maybe 10 is this. No, this doesn't work. If I increase, no, this doesn't work anymore. 11, 3.6. Okay, so now with this kind of strategies, there is no optimal strategy for valuation 10 guy. So this doesn't work like we wanted it to work. So the first equilibrium we found was good, but now that I attempted to find another equilibrium, when A is 8, it no longer works as well as I want it to. Yep. Sorry. Okay, maybe this will work. A8, B10, then let's try it. So let's try this. So C11 now works. Okay. C11 now works. And what about D14? No, D14 doesn't work because 12 is obviously dominating. 12 is dominating. So D12 works, but now this may have messed up this player again. Yep, it messed him up, and there may not be. Oh, it actually C12 now works, but this probably messed up the fourth guy. Yep, it messed him up. So as you can see, when I chose A8, I went on a wild goose chase and I couldn't find a Bayes-Nash equilibrium. But if I had chosen A9, then it was actually easier to find the Bayes-Nash equilibrium. So I actually found it in this case, but in the previous case, I couldn't find it anymore. So in my searches, so 13, 12, 10, and 19. So this 9, 10, 12, 13, as I tested with this desmos graph, is a Bayes-Nash equilibrium, and when I tried to find another one, I couldn't find it. But you can play with this desmos graphs. I'll provide their link in the description. And yeah, you can try to find if there's any other one. That's it.